let me go ahead and start. Welcome everyone. So today we're just going to continue doing mesh analysis. Last time we introduced mesh currents and how we can use these fictitious currents for the sake of solving more elaborate problems. And in fact, it tends to be a very good, very efficient, very fast way of solving a lot of circuits. And you can actually write those equations quite quickly just by looking at the circuit, and then you just have to solve them. Okay, so let's go ahead, let's continue with mesh analysis. And let's give ourselves a bit more elaborate of a circuit. So this one will have two voltage sources in it. We'll do a 12 volt source. We'll do an 18 volt source. We'll do a 2 ohm resistor here. We'll do a 5 ohm resistor here. 3 ohms, 4 ohms, and we'll do 2 ohms. Okay, and so being a procedural, very programmatic, very formulaic way of solving these circuits, we'll go through and run through those steps. Step 1. Step 1, assign mesh currents. Okay, so looking at this circuit here, I see 3 of these so-called windows. So I will have 3 mesh currents. I'm going to arbitrarily pick them to just go in a clockwise fashion for each one of them. I'm not going to think too hard about this. There's no benefit to writing them to go in opposite ways or anything, and it doesn't matter. So I'm just going to do IA. I'm going to do IB. And I'll do IC. And you can see here that 2 of our mesh currents, IA and IB, have a voltage source involved in their loop. However, IC does not. Either way, we're going to end up with 3 equations. So that takes care of step 1. Let's go ahead and let's move on to step 2. We'll write our equations. And I'll put in, and especially pay attention to source polarities. Source polarities, I'll just abbreviate that. And when I say pay attention to the source polarities, I'm saying make sure you pay attention. This is positive, this is minus, this is positive, this is minus. Okay, so now we'll go ahead and write out these equations. We'll start with the first equation for our IA loop. I'll just denote that with a semicolon here so that I know this equation refers to the mesh current IA. I have seen mistakes in exams in the past where somehow this ends up being part of the equation. This is not. I'm just using this to designate that this equation refers to our first mesh current. Okay. And now I will pick a point and I will follow the mesh current around and I will write out a KVL expression. So I'll invoke Ohm's law in order to give me the voltage drop of each one of these components. We have 4 components in here. So I'll start with the first one, 2 times IA. All right, I'm done with that. Let's move on to 3. I have 3 IA. However, IA is not the only current that is involved with this 3 ohm resistance. We also have an IC going through it. So make sure if you have 2 mesh currents involved in a component that you include the other voltage. Now, at this point, we need to look at the direction here. IA was going through, downward through this 3 ohms, whereas IC is going up through 3 ohms. IC is going in an opposite direction of IA. Therefore, we will subtract this voltage. So minus 3 IC. Okay, we'll move on to the next one. We're done with the 3 ohm resistance here. We're following the path of IA, and now we have this 5 ohms. So plus 5 IA. Now, IA is not the only one involved with this 5 ohms. We also have an IB. However, notice IA is going to the left, whereas IB is going to the right. Since they're going in opposite directions, we'll subtract the 5 IB. And as we continue following the path of this mesh current, the polarity that we hit of our 12 volt source is a minus. So I will take that to be minus 12 volts. We're back at where we started, and KVL says the sum of all voltage drops in any closed loop is equal to 0. Therefore, this whole thing is equal to 0. Now, one thing I want to bring out is notice that with respect to the IA mesh current, all of our voltages are positive. When we followed this IA around, it was plus 2IA. When we hit the 3 ohms, it was plus 3IA. When we hit the 5 ohms, it was plus 5IA. So you can always count that the mesh current, the voltage that we are writing with respect to this mesh current, is always going to be positive for the components that IA refers to. So if we're writing an equation for IA, we're always going to have plus 2IA, plus 3IA, and etc. Okay? Even if you reverse it, yeah, absolutely. Check this out. Great question. Let me do something here. Oh, did I really just draw all that so that I could put my arrow going in the wrong direction from what I wanted to do? Yes. All right, I'll cover up the head of that arrow. I will make this one go backwards. And this one, I'll keep going in the same direction. And let me get my values here so that I can show you 2 things. Okay, and actually, in the original problem, I did forget to put the value for the bottom here. This is a 1 ohm resistance. Okay, but nevertheless, I wanted to show you this because actually, well, 3 things. Let's go ahead and write out that equation for IA. All right, pick a point, any point. Let's start with here. And let's just follow around. What's the first thing that we encounter? 3 ohms. Well, since we're writing the equation for IA, the voltage is going to be positive with respect to it, because in all instances, when we write this equation, we're following the current. So it doesn't matter which direction it's going in, the voltage is always going to be positive with respect to how we write our equation, because we are writing our equation following the mesh current. So if our mesh current's going counterclockwise, as it is in this case, or if you're from Europe, they have a tendency of saying anti-clockwise. So if you're following it anti-clockwise, you're going to get 3IA. Okay, so it's still positive with respect to the mesh current equation that we're writing out. However, now I'll show you another thing. Notice that IC is also involved when we write out the voltage for IA going through this 3 ohm resistance. We also have to include IC. IC is now going in the same direction. IA was going upward through the 3 ohm resistance. IC is also going upward through the 3 ohm resistance. So at this point, it is now plus 3IC. Okay, so two things that I just showed. The fact that the voltage with respect to IA is still positive even though we reverse the direction of the mesh current, but also because now both of these are going in the same direction, we add the IC to that. And let's actually finish up this loop. Okay, let's go through, and we have this 2 ohm resistor, so plus 2IA, still positive. And now notice the other thing that changed about this. If you notice, our mesh current is now going into the positive side of our 12 volt voltage source, so plus 12. But notice we didn't finish our loop once we got to the other side of our 12 volt source, because I started over here. If you need a little reminder, feel free to just put a little dot where it starts. Okay, and now I have this 5 ohm resistance over here, so let's follow around, and I get plus 5A, still positive with respect to IA. But we also have IB involved in this 5 ohm resistance, and IB is going to the right. Well, IA was also going to the right. So again, we will have to add these two voltages. So plus 5 IB. And now we're back at where we started, so set the whole thing equal to 0. Okay, so that's how we would write this expression in the case of, if we picked it to go in the other direction. Now, I advocate for writing them all to go in the same direction. And I advocate for writing them all going in a clockwise fashion. And the only reason for that is just so that you're practicing the same thing over again. Less likelihood of screwing up something if you do the same thing over and over again, right? Practice makes perfect. Not really. Perfect practice makes perfect. Okay. So, yeah. So let's go ahead and let's actually continue with my original version of this. And now let's write out let's go ahead and write out IB. Okay, for IB, actually, let me go ahead and give myself some space here so I can reduce this equation afterwards. Let's do IB now. Okay, for IB, I'm going to do the same thing. Start over here. I get 5 IB. However, IA is also involved. It's going in the opposite direction, so minus 5 IA. Keep following IB around. We now hit the 4 ohm resistor, so plus 4 IB. IC is also involved. It's going in an opposite direction of IB, so minus 4 IC. Keep going around. We get plus 1 IB. And now we hit the voltage source and we hit a minus 18. And we're back at where we started, so set the whole thing equal to 0, and KVL, Kirchhoff, laying in his grave, should be happy. Okay, now let's go ahead and let's write out the IC expression. And as I mentioned earlier, there's no voltage source involved here, so we're just going to not have this voltage standing on its own inside of the expression. We're just going to get an expression that's only in terms of, IC, IA, and IB, and these resistances over here. So let's pick a point, any point. Let's start over here and continue following that mesh current. The first thing we hit is 4IC. However, we also have IB involved. IB is going opposite of IC, therefore minus 4 IB. We're done with the 4 ohms. Keep going, and notice now we hit the 3 ohms, so 3 IC. IA is also involved, going in an opposite direction, so minus 3 IA. Keep going around. We hit the 2 ohms plus 2 IC. And we're back at where we started. Set the whole thing equal to 0. Now let's go ahead and let's reduce these equations. Let's go ahead and gather up our terms. So I'm going to gather up the IAs first. I have 2 IA plus 3 IA, so that's 5 plus another 5 IA, so I have a grand total of 10 IA. Now searching through my IBs, I only have 1 IB here, so minus 5 IB. Now I'm looking at my ICs, and I have a minus 3 IC. That's the only one. And I'll take my voltage and shove it to the other side of the equation. So add 12 to both sides. We get equals 12 volts. And we are done with our first expression. Okay, let's do the same for the next one. I'll gather up my IAs. I'll line them up so all my IAs are on one, are lined up with each other, all my IBs, all my ICs, etc. So let's go ahead. I have a minus 5 IA, and that's the only one. My IBs, I have 5 IB and 4 IB and 1 IB. Looks like I have 10 IB. And my ICs, I only have 1 in here, so minus 4 IC. And I have a minus 18 volts here, so add 18 to both sides, and I get equals 18 volts. And I have my second expression. Let's go ahead, let's do the last one. Okay, IAs, I have one term of IA, which is a minus 3. So minus 3 IA. For my IBs, I have a minus 4 IB. And I have, that's the only one. And my ICs, I have, let's see, 4, 7, 9. So plus 9 IC. And all of that ends up being equal to 0. Cool. Okay. So all those voltages add up to 0. Cool. Okay, so now we have three expressions. Now we have three equations, we have three unknowns, so we can solve the system of equations to get the values for IA, IB, and IC. There are many methods to do this. I will list out these methods here. With two, it is very straightforward and easy because you can just solve one, and then for one of your variables, plug that into the other equation, get one of them. So you can just use substitution, and you can use substitution with these three, but it starts to become a lengthy process that's prone to error, especially when you're trying to do things quickly. So I'm going to list out the methods that we have available to solve for us. Okay, we can definitely use substitution. We can add / subtract equations. That's another method. There's a matrix method to do this as well. I think the matrix method in along with your calculator might be the least error prone and probably the best for an exam. Some calculators also have the ability to just punch in three equations and hit solve system. I know my TI-89 does that. So let's say matrix method with or without calc. Calc method with the calculator. Maybe a solve function. And there's some great online tools that you could use to verify the output of any of these, which would be using something like Wolfram Alpha. I actually really like using Wolfram Alpha because it always lists the steps involved with different methods for how to solve. So that tends to be useful for me because not only do I get the answer, but I can also go back and see how it got the answer. And I tend to get a little better at math doing it that way. So I don't want to, strongly advocate or anything, but I do appreciate that Wolfram Alpha acts a little bit like a math tutor for me. So these are all of our methods. Now, for the matrix method, I have a link on my website. So let me go ahead and pull that up. Where's my web browser? There it is. Okay. And let me switch over from here to... If you go to my website, 211, and you go down to lecture videos and other resources, solving a system of equations with matrix, and it's from this cheesy website, Math is Fun, and they have an example here with exactly three variables and three equations. So exactly what we just did. And in fact, I will usually not give problems on an exam that has more than three variables. And if it does, it tends to be very easy in that one of them can be solved that one of them is actually almost given. But yeah, I'll talk more about that when we get closer to exam time. But nevertheless, you line up your equations just as we did with the IAs and the IBs lined up like this, right? So we line all that up along with the what's on the other side of the equal sign. So over here, 6 minus 4, 27, like this. And then you can turn it into a matrix where you take out those coefficients and plug them into a 3 by 3 matrix. And then you can go ahead and solve using the dot product, and you can get your answer here at the end of the day. I think this along with your calculator is probably the most least error prone. Or if you have a system of equations solve button on your calculator, that works well too. I have no requirements of using specific calculators, or you can't use graphing calculators. And during this semester, it's kind of a moot point because I'm not going to tell anyone on an exam that you can't use Wolfram Alpha because, you know, I have no way of enforcing that. So if you want to use a web-based Wolfram Alpha calculator, you're free to do so. Okay, so let's go ahead and let's get back to our specific problem. I just point out these resources, and depending on what calculator you have, I guarantee you there is a YouTube video that exists for your specific calculator. So you can always search YouTube for your calculator. Okay, and so I would definitely advocate go ahead and do that. Learn how to solve these system of equations in the fastest way possible with the least amount of error by doing a little bit of your own outside research, and you can always refer to that page that I linked on my website for how to do it with matrix. What time is it? We have about 18 minutes left. Now, I have already solved the system using the add subtract equations method over here that I listed. I'll go through this rather quickly, but I lined up probably, let's see if I can. Do a little zoom on this. Might be a little hard to read. Let me adjust the that looks better. So I get my three equations. I add the A equation and the B equation. I probably should have had this listed as IA and IB. Maybe I'll make a note to myself. Oh, hey, look, if I just do this. Problem solved. Okay, I take my IB equation and my IB and IA. I add them together to cancel out one variable. If I multiply my A equation by 2, I'm going to get a minus 10 IB. Oh, wait a second. Sorry. I'm looking at the wrong equations. If I take my A and B, and I multiply the second equation by 2, I will get a minus 10IA. That'll allow me to cancel out the IA terms. I end up with this expression that I have canceled out IA, and I'm left with just IB and IC. I then subtract IC from IB to try to get rid of IA. And then I end up with, if I multiply my B equation by 3 and multiply my C equation by 5, I can get rid of my IA in my second two equations. And I end up with this formula, and then I can go ahead and now use both of those to cancel out one of my terms. I end up with my IC, and I have a value for that. Now I can go ahead and substitute my IC back into one of these equations. I get my IB, and then I can plug my IB and IC into the original equation to get IA, and I get that. Okay, so several different methods in order to solve. I think the most important part is that you just practice whichever method you plan on using and make sure you can do that consistently with the right answer. And you can always verify those using another source like Wolfram Alpha. So if I wanted to go ahead and get some practice punching it in as a matrix into my calculator, have my calculator do the heavy lifting of doing that dot product while I just enter it in as a matrix, then I can verify that with Wolfram Alpha. Now I have two independent sources that are giving me the same answer. I know it must have been done right. Okay, so regardless of how you get the answer, let's get back to the whole purpose of doing this. I gotta fiddle with these clamps to hold my camera in place. And I will fix the focus. Configure video. Focus, I'll bring you back down to 5. There we go. Okay, so let's go ahead and write out what these values ended up being equal to. We ended up with an IA equal to 6.275 amps. We ended up with a mesh current IB equal to 7.023 amps, and we ended up with an IC equal to 5.213 amps. Okay, so those are the values for our mesh currents after you solve the system of equations. Okay, so now we're going to use these fictitious tools, these mesh current values, in order to figure out our real currents going through this circuit. So at this point, let's rewrite the circuit and then translate our mesh currents into real currents. You got 0.213 for IC. You see? Yeah, it's very easy to get to mess up those solutions. So make sure to practice that. It's too easy to mess up, and I don't want people losing points just because of messing up little calculations like that. I want people to get full credit if they understand the analysis technique that we are learning. At the end of the day, what matters in this class, to me at least, is that we can go ahead and apply this mesh analysis technique. Okay, let's go ahead and let's redraw our circuit. Two ohms, 5 ohms, 1 ohm, 3 ohms, 4 ohms, 2 ohms, 12 volts, 18 volts, plus, minus, plus, minus, and can I fit this all in? I bet if I fold the top, that's the one thing I do not like about remote teaching, is that I just don't have a whiteboard big enough for what happens in these classes. All right, I think we can see everything now. Perfect. Let me make my head smaller. There we go. Okay, so let's go ahead and take a look at each one of these components. We'll go through it and we'll look at what the mesh current is doing and what the value is. IA is going to the right through this 2 ohm resistor, and IA has a positive value of 6.275. The fact that we have a positive result means that the real current is going in the same direction as our mesh current. Now, as far as this 2 ohm is concerned, the only current involved is IA, so that's the only value that matters, 6.275 amps. Okay, let's go through and let's take care of all the ones that only involve one mesh current. So let's go through. This one had 2, this one had 2, this one had 2. I'm just getting the easy ones out of the way first. This 1 ohm only had IB going through it. IB was going to the left, and IB had a positive value, which means the current is going in the same direction, and we had a value 7.023. Okay, let's go ahead. And the other one that only had one mesh current involved was IC, and we have the value for IC. It ended up being positive, so it will go in the same direction as our mesh current with a value of 5.213. amps. Okay, now all the other components had multiple mesh currents involved. So let's go ahead, let's start with this 5 ohm resistor here. Now the 5 ohm resistor has, and I'm going to draw this off to the side here just to make it a little more apparent. This 5 ohms had 2 mesh currents involved. It had IA. IA was going to the left, and it's positive, so it goes in the same direction with 6.725. However, it also had IB, and IB was going to the right, and it has a positive value with a magnitude 7.023. Notice that that's larger than 6.725. Both of these are amps. Okay. Now, notice we have 6.725 amps going to the left and 7.023 amps going to the right. The one going to the right, the 7.023, is larger than 6.725. So our result when applying superposition is going to be to the right. And we can just subtract the 6.725 from the 7.023. You will get 0.748 amps of current going to the right. Okay, so I draw it off to the side just to keep my sanity while I'm doing this and get all of my directions and magnitudes correct so that I can understand what I'm looking at. Okay, let's go ahead. If there's no questions, are there any questions on how I did this over here? Cool. At least one person doesn't have a question. Do the other 32 people? Oh, cool. Okay, perfect. I don't need 30 responses. I'm just being facetious and having fun. Okay, so, oh, now everyone's chiming in just because they want to. I see how it is. Okay, so let's... Thank you for that. Okay, let's go ahead and let's look at the next one. We have 3 ohms. Now, as far as this 3 ohms is concerned, we have IA. IA was positive. It's going in the same direction as the mesh current, so it's going down with a value of 6.275. Sorry, I'm squeezing that one in there. It also has mesh current IC involved. It is going up, and it's a positive value, so it'll go in the same direction, 5.213. And if you notice, the one going up is smaller, so the resultant current is going to be down. And we will just subtract 5.213 from 6.275, which will give us 1.062. Okay, we're on to the last one. Sorry, I just looked back and I saw all the no's and I thought I screwed something up, and then I remembered, oh yeah, I asked if people had questions. I was thrown off for a second. Okay, now we have our last one, which is this 4 ohm resistor. I will also draw this over here. And let's see what the currents involved with was for that. We had an IB going down with a magnitude of 7.023. It's positive, so it will go down. The current is going down. just like this lecture. Okay, and we also have an IC that's going up with a positive value of 5.213. All right, so at that point, we know that the larger one's going to win. Result will go down, and we will subtract 5.213 from 7.023, and we get the value 1.81. All right, that's our actual current. That's our real current. We now have everything that we need to finish up this circuit. If you want to go ahead and find out what the voltage drops are for all of these components, and why not, let's go ahead and do a couple of these. I have 2 ohms with 6.275 going through it. I'll throw my calculator over here to the right side, and I'll do 2 times 6.275. I always enjoy more Ohm's law practice. I feel like there just isn't enough, right? .55 volts. Let's do this one over here. We have 3 ohms times 1.062 amps. 3.186. And let's do this 5 volts over here. This 5 ohm component over here. So 5 ohms, V equals IR, so just 5 ohms times 0.748 amps. We get 3.74 volts. Okay. Now, I'm only going to do these so that I can do at least one Kirchhoff voltage loop and show that the sum of all voltage drops in any closed loop should be equal to 0. To help me out with this, I'm going to pay attention to my polarity. Current always, 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 always goes from a higher voltage to a lower voltage. Current always goes from a higher voltage to a lower voltage. And if you're ever lost while you're solving a problem, tell yourself, current goes from a higher voltage to lower. Okay, now let's go ahead and follow this loop and let's see if this works out. I really hope it does. Otherwise, I'm going to be in trouble. Okay, so I'm going to start at this point. And I'm going to go all the way till I get back around to that. Here's one enclosed loop, so KVL should hold true. So I will do plus 12.55. Keep following around. The first polarity I hit, plus 3.186. Keep going around. Oh, look at this. We hit a minus first. Minus 3.74. And I go around and I hit a minus 12. And I'm back at where I started, set the whole thing equal to 0. So as long as I'm not lying to you, I should be able to punch that into my calculator and get the have it actually be equal to 0. So 12.55 plus 3.186 minus 3.74 minus 12. And I really hope this is at least close to 0. Close enough for government work. Okay. So, yeah, we have a little bit of a rounding error. Previously, when I did these equations, I'm sure I rounded it out to 3 decimal points. Pi equals 3 situation. We're not off by that much. 6.275 amps. What about 6.275 amps? Did I wrote down 6. Did I swap? Okay, well, let's take a look at this. 6.275. You're talking about this one. You did the right number. 6.275. No, I think I'm right. Oh, at the top right. 6. Oh, you're right. You know, I'm learning something about myself. I am learning something about myself. I think I have a tendency of swapping numbers in my head, because when I think of a number and then I go to write it down, it's something I have noticed ever since my early days of university, that I've always been doing that. And so that's why for me, it always helps do stuff graphically. Yes! Mesh analysis is kind of a faster way to get superposition, or at the very least, you're using elements of superposition under the technique, right? The technique relies on superposition in order to work. That's why we can make up this concept of a mesh current, because we know that as long as we write it out, we can eventually apply superposition, and it will take into account both of these. Yeah, absolutely. Superposition is kind of what makes a mesh analysis work in the first place. Cool. Okay, so with that being said, let's go ahead and head off to lab. I'm going to stop recording.